All right, welcome to the review session. So not a ton of people here, so we'll just kind of address everybody's questions kind of in turn as they come in. Hopefully more people find their way to the Zoom by the time we get to the end of our time here. But the first questions we wanted to address came from inside the room here. And they were specifically about Haworth structures and Fischer projections and kind of what we need to do with them. And so the important thing to know, and I believe I put this into the study guide, and if I didn't, then I'll make the adjustment. But as far as chapter 13 is concerned, there isn't anything in here about needing to be able to draw Haworth structures. We did that as an illustration in class because there were a couple of homework problems about that, but you don't need to be able to draw them. Same thing with the Fischer projections. I'm not requiring you to know what galactose looks like versus glucose. That's not what we're about. Now, at the same time, you do need to know, what the pairings are for some of the disaccharides. So you need to know that sucrose is glucose and fructose. You need to know that those two together make sucrose. You need to know that maltose is two glucose molecules together. So those are the things that you need to know. But in terms of, okay, draw me a Fischer projection for glucose, I'm not going to ask you to do that. What I am going to ask you to do is, if I give you a Fischer projection of glucose, can you tell me that it's D or L? If I give you a Haworth structure, can you tell me if it's alpha or beta? And so just to remind ourselves of what those look like.
Do you understand like the left one, between the L and one, like from the left and the OH, but it's just for the alpha beta.
Right. So in the Fischer projections here, we're always looking at that last hydroxyl group and its position. So the D enantiomers all have it on the right-hand side, the L enantiomers all have it on the left-hand side. That part's pretty easy to kind of pick out and figure out. It's the tougher one is because we didn't spend nearly as much time with the Haworth is I don't even have an example here. For the Haworth, what we're looking at is a different kind of positional piece. So for that, let's go to just our chapter 13 lecture. And so when we're evaluating alpha versus beta, what we are looking at is we are looking at the carbon that is adjacent to that oxygen in the ring. So the one carbon. Alpha versus beta is an up versus down. The beta position is in the upper position. So this is beta D glucose here. And you can see it's beta because that OH group is in the up position as opposed to the down position. If these two were switched, if it was H on top and OH on the bottom, then it would be alpha D glucose. So alpha versus beta is up versus down, or more precisely down versus up.
So it's only with that one then? only the one on the right.
Yeah, so it doesn't matter if you're looking at a 6-member ring or a 5-member ring, the result is the same. It is the carbon immediately adjacent to that oxygen. So we usually depict that on the right-hand side. And so again, beta is up, alpha is down, and that's really the only differentiating factor that you need to know is that up versus down, left versus right. And the good news for you there as well is you can't determine if it's beta D or beta L unless you have the Fischer projection first. And since I'm not requiring you to convert Fischer to Haworth, you're not going to need to know that. So it's really more a matter of, if I give you a Fischer projection, can you identify D versus L? If I give you a Haworth, can you identify alpha versus beta? It's not going to cross the two. So I can give you a Haworth and ask you, okay, is it beta or alpha and D or L? It's going to be, we're going to separate the two.
About the Fischer projection, so when you're doing the mirror image, is it the whole thing is mirrored, or is it just the hydroxide? It's the whole thing.
It's the whole thing. It's the whole thing. So when we talk about the non-superimposable mirror images, you can see, so here in this example, DNL ribose, DNL glucose. The only things that are not flipped are those cap carbons, the end carbons. Otherwise, yeah, it's the chiral carbons that we're concerned with in terms of that superimposability, non-superimposability. So whatever carbons are kind of in the middle of that Fischer projection, those are the ones that are going to flip around.
Can you go back to the practice quiz with the heavy enantiomers on the
Okay.
So you're doing like opposite D glucose to project, it would be L glucose, it would be, I'd have to write it down, but.
No, it would be L glucose.
It would be?
So if I'm looking, here's D glucose, this one right here.
Yes.
So if I'm looking for the enantiomer, I'm looking for that non-superimposable mirror image. So I should be able to put it and its other enantiomer side by side, draw a line in between, and say, I should see the exact same thing on the other side of this plane. So I should see an OH on the other side of this plane. I should see an H, an OH, an OH, and we've got the aldo group here and that 6th carbon alcohol group there. So these are enantiomers of each other. They're the same molecule. To be an enantiomer, you have to be the same molecule. So right away, your head should immediately say, if I'm looking for the enantiomer of D glucose, I need another glucose. So fructose is out, idose is out, galactose is out. The only one that would even make sense is the glucose. It has to be the same, it has to be an isomer. It has to have the same chemical formula. And it has to be a mirror image. And so the easy way to do that again is put that mirror plane in between, and you should be able to see matching across that mirror plane.
Okay, I confused myself. I see it, yeah, it's just mirrored.
Yeah, that's all an enantiomer is. An enantiomer is a mirror image.
I confused myself, and it was like, I was thinking that was weird, but it's still the same thing.
Right. The only difference with these mirror images is that they're non-superimposable. So if I were to drag this L-glucose on top of the D-glucose, the groups wouldn't match up. So they are mirror images, but they don't line up with each other.
We jump ahead into lipids now.
Sure.
I just need to know like the categories really, because that's one of the quiz, and I kind of bubbled those a little. Yeah, it's like which one is how do you look at it and know it's like the wax or
Okay, so if we're looking at our categories of lipids, we would say that they fall into kind of 4 main categories. There are the waxes, there are the triglycerides, fatty acids. So we'll actually break it into 5. Triglycerides, the phospholipids, and then the steroids. Those are the 5 categories, and really these first 4 categories all have at least some common threads to them because all of them have ester linkages somewhere in them. What makes a wax is that we've got that ester linkage, and on this side we've got usually an amino alcohol, and on this side we've got just your normal fatty acid chain. So you just got hydrocarbon on this side. So one of the reasons why we're getting a little bit confused by waxes is we really didn't say too much about them. And actually, I misspoke. It's not an amino alcohol. That's on the phospholipid. So basically a wax is a big ester. That's basically what it is. So let me go back to the whiteboard here. Let's fix that. So when we bring together a fatty acid and a large alcohol to make an ester, that's a wax. And so in total, we end up getting somewhere between 14 and 30 carbons in the whole thing. So, if we're thinking about our fatty acids, we're thinking like your stearic acid, your oleic acid, your palmitic acid, whatever the case may be, you've got 14, 16, 18 carbons in this acid. And then you also have put that with a large hydrocarbon. So, something on the lines of octanol, decanol, something with, 6, 8, 10 carbons on it. And so you put those two together and you've got, somewhere around 20, 25, 30 carbons, depending upon the size of each of the pieces. So this is like a superester. It's big. And because it's big, we're losing the polar quality of the ester to the large non-polar quality of the hydrocarbons.
So full, so you draw a full, so on the test, so when you're given like, I don't know if I can, but it just gives you something that's like what this is, or maybe one of those things that, right, like.
There are going to be some of those. So yes, on the quiz, yeah, that question about the wax, a lot of you missed that one, mistaking it for a fatty acid, but there wasn't an acid.
So if, so what was full wax, it would just, I don't know what they like look like. I see like this, but like a full like example of an actual like wax.
So if we were looking at an example of a wax, so you've got the long, I got lazy there at the end, but you've got a long chain of hydrocarbons representing the fatty acid. You've got a long chain of carbons representing the alcohol portion. In total, you've got, again, by definition, according to what's in the book, 14 to 30 carbon atoms. So we're talking about, this is more than just an ester, where most of the esters we talked about in chapter 14, it was like, a 5 carbon acid and a 3 carbon alcohol, a 6 carbon acid and a 4 carbon alcohol, relatively small chains on each side. You're going to have big chains on each side. So for all intents and purposes, a wax is an ester, but it's a supersized ester. And if we compare that to just fatty acids, we don't have the ester part. What we have instead is, for fatty acids, it would be basically just a long chain acid. So it has to have the acid group on the end. And so that's what separates the fatty acid from the wax. There's no ester part. Now, this fatty acid chain could be unsaturated or saturated. So there could be one or more double bonds in there as well. And that's where we get into differences between, oleic acid and, palmitic and linolenic acid, and the number of double bonds inside of that structure. Triglycerides, we have to have glycerol plus 3 fatty acid chains. So this is almost like a triple wax that's been connected. Because with glycerol, we're getting the 3 carbon backbone. and then it's getting connected to some kind of fatty acid group here. And again, those fatty acid chains are going to be long, starting with somewhere around 12 to 14 carbons, could be saturated, could be unsaturated. They would all be triglycerides.
Triglycerides. When you do the hydrogenation reaction, that just turns all the double bonds to single bonds.
Correct. Correct.
So it's
So
only for triglycerides and fatty acids. It doesn't take for anything else, right?
correct. So yes, you could do a hydrogenation reaction with a acid and turn it into an alcohol or a double alcohol. That isn't as much as what we talked about. We talked generally with hydrogenation. So going back to chapter 14, most of the hydrogenation reactions we were looking at focused on double bonds. We really didn't talk too much about any of the reactions with carboxylic acids other than esterification. So that's where I want you to kind of focus that attention. Hydrogenation, we're going to talk about alkenes turning into alkanes. So, you know, that double bond somewhere in that fatty acid chain turning into a single bond, turning the saturated, or excuse me, the unsaturated into saturated, not turning a carbonyl group into an alcohol group. That's a different kind of reaction. That was something we talked about last test when we got into oxidation and reduction of carbonyls with ketones and aldehydes that way. That's a different conversation. So phospholipids, remember phospholipids come into two different kinds. There is the glycerophospholipid, where we basically take this glycerol structure and we swap out this last fatty acid group for a phosphate group. And an amino alcohol. That's where the amino alcohols come in. And if you looked at the prep sheet, study sheet, what you should see there under the materials, I'm giving you all of the different acids. I'm also giving you those 3 common amino alcohols so that you can recognize them, not so that you can use them to identify, oh, this is lecithin versus something else, but more so that you can recognize, oh, this is attached to a glycerol group, it must be a phospholipid, as opposed to just a normal triglyceride. So that's what these are for. That's why I'm giving them to you here. So that's the glycerophospholipid. And then there's the sphingomyelin, which we've got this bottom group as well. We only have the one amino acid, or excuse me, we only have the one fatty acid group. Instead, we get the carbon group here. That's related to the sphingosine. So the top one is set, the bottom two vary.
So what does this sphingosine look like again?
So it is, one of the differences is it has a nitrogen in it. So your sphingosine here, you're going to get an amide linkage. So it's not going to be glycerol. It's going to be sphingosine. Sphingosine has a nitrogen group in that middle position instead of an alcohol group. And so you end up making an amide bond instead of an ester bond in the middle there.
Yeah, something on this.
And then finally, steroids.
Yeah.
Steroids we can always pick out because they always have that steroid nucleus.
Cholesterol, that's a steroid, right?
Correct.
Okay, I did not. There's something about. So the different like types of cholesterols.
So,
Yeah.
okay, so cholesterol really, what we call cholesterol is this molecule here. But what we understand is that lipoproteins take that cholesterol. So the cholesterol molecule is here. So yes, cholesterol is a steroid. That's its structure there. And so where we can get confused, on a blood panel, it'll give you LDL and HDL, which we tell you are the good cholesterol and the bad cholesterol. The cholesterol really isn't different. It's really the lipoprotein that we are concerned with. And so what you can see here is the lipoprotein. This is your cholesterol group. Attached to it is this ester bond that we can vary. And if we take these esters, the cholesterol esters, and link them up to these lipoproteins, these phospholipids, that's what can allow us to transport that cholesterol in and out of the body systems. And so it is these that are going to kind of make the difference for us, because the ones that are low density, the LDLs, the low density lipoproteins, these are the ones that carry cholesterol from your liver to the rest of your body. And it's the high density ones that take the cholesterol from the rest of your body and bring it back to your liver. And if it's in your liver can process it, synthesize it, break it down, and excrete it, take it out of your body. So the reason why HDL is so useful and so important is because its job is to bring it down and help your body get it out. And so if you have too little HDL in your body, then that impedes your body's ability to process cholesterols properly, and that can lead to an elevated cholesterol level in your body. So ultimately, HDL takes the cholesterol from your body into your liver. From your liver, it can get processed out in bile salts, which make its way out through your waste systems. HDL transports from your liver to the rest of your body, and if it gets into your bloodstream, that's the excess cholesterol in your bloodstream can cause plaque in your arteries, can cause other kinds of issues if there's too much. So when we're talking about cholesterol, the molecule itself is a steroid. In terms of how your body uses it and how we kind of classify it, HDL versus LDL, that's the lipoprotein. That's the transport system that's being described there.
Difference between fat and oil, like, do they look different when you draw them out, or is it just like?
So they're all triglycerides. The difference between fat and oil is the phase. Fats are solid phase triglycerides. Oils are liquid phase triglycerides.
So you can only tell the difference, like when you draw it like a formula, you couldn't tell, but like you saw it and realized.
Well, we can tie it to unsaturation. Saturated triglycerides, because they can stack better, are going to have a higher melting point, which means they're going to be solids. Unsaturated triglycerides, because they won't stack as well, are going to have lower melting points and are more likely to be liquids. And so that's the difference. So we can look at it from a formula standpoint, because all we need to look for is saturated versus unsaturated. Saturated triglycerides are fats. Unsaturated triglycerides are oils. So all I need to look for is a double bond. Any presence of a double bond is going to move into the oil category compared to the fat category. But they're all triglycerides.
Those are the main things I have. I can't really think of anything else that's like sticking out to me that I want to go over. I think we don't have any check functions. The little 13
Which kind of makes sense, because chapter 14 was mostly used to just kind of set the table for 15, introduce you to all the functional groups, introduce you to a couple of reactions that we later used more fully in 15. So that makes sense. It's
a lot.
okay. All right, Sean, you still with us?
Yes, sir, I am.
All right, was there anything that you wanted to hear specifically? We kind of just bounced around 13, 15 a little bit.
No, I had some takeaways from that. Sorry, I'm just also at work, so I'm listening in. But
I
no, I'm
I
pretty good.
understand. I'm about to close things up. If there's nothing more. That's why I'm asking.
No, sir, I don't have any questions.
Okay. All right, then we'll shut it down here. Thanks for being here. I'll see you on Tuesday.